Welcome to the lecture on modeling considerations for inclusion removal in Tundish. So, we discussed about the various aspects the way Tundish performs, and one of the important work that is desired from Tundish is the inclusion removal. As we know that in the continuous casting process, the ladle will be delivering the steel to Tundish, and then from Tundish it will go to the mold. So, basically when you have if this is the ladle, and then from here it will be going to the Tundish. So, this is your Tundish, and then from here it will be going to different molds. So, basically the inclusions may be there in the Tundish that may come from the ladle, that may be formed also because of the reaction products, that may be formed because of the erosion from the Tundish lining. So, there may be different reasons because of which there will be inclusions that will be there in the Tundish. Now, the thing is that Tundish needs to be taken care of. Tundish needs to take care of the inclusion in the way that if this is the last reservoir, after that if the Tundish if that inclusions in the Tundish goes through this outlet and in the mold, then it is likely that it will go into the cast product, and that will be permanent damage, basically that will be basically leading to the rejection of the product. So, this is the last reservoir, and that is why its function becomes very important, that it should remove the inclusions from here. Now, as we know that the inclusions will be of normally they will be of lighter density than the steel, and they will have very fine sizes. So, in the micrometer ranges their sizes will be varying. So, they need, so basically it is to be understood that what are those mechanisms, what are those theory which will govern the removal tendency of the inclusion or the flotation tendency of the inclusion, because these inclusions depending upon the flow configuration inside the Tundish, they will be it will be desirable that they float towards the top free surface, and on the top free surface they are likely to be trapped because you have a slag layer. So, that may trap these inclusions. So, that is most likely, else they may go and stick to the walls also, depending upon conditions which is prevailing inside the Tundish. So, basically being lighter than the liquid which is there inside, it will be subjected to the buoyancy, and that force will be acting on it. So, they will have the tendency to float up. That is what we discussed in our last class also, that gravitational effect and the buoyancy effect will be very much applicable in these cases. Then so you will have basically the way on the inclusions, one will be forced because of the velocity of the existing liquid which is there, and in that there is these particles. So, because of that fluid velocity component of the fluid, another will be because of the rise velocity of the this inclusions. So, there are two components which will be responsible for its for the so they will be interacting each other, they will be interacting on the inclusion particle, and accordingly in a resultant manner the inclusion will move inside the domain, and then either they may go through the Tundish outlet, or we will feel that it will be desirable that it goes towards the top free surface. So, we will talk about it now why it is. So, that is why we need to do the modeling of this, we need to also develop the similarity criteria for that. We need to know the parameters which are of significance, how we should take the density, or how the depending upon the scale factors, how these inclusion removal tendency can be predicted or can be modeled using water modeling or even mathematical modeling. So, that needs to be studied, and there needs to be some concept on this topic. So, if you talk about the studies of inclusions, so what happens that inclusions, you will have the normally the non-metallic inclusions, and they will be varying in sizes, and also that can be modeled by the water modeling technique also. We can do in our laboratories, where we make the perspex Tundish from perspex sheets, and there also we can think of having these inclusion particles as either these polyethylene particles or so, or maybe vinyl silane or so. That has been reported by the researchers that these particles are used, and they have also size ranges. So, that can be used for the study, and people can inject it in the form of so. So, the simulation of the removal of inclusions in water model has been carried out with different particles in the size range of 20 to 150 microns. So, that is reported in the book written by Sahai and Emi, and they have reported that they have done also, they have also done these simulations, and there they have varied those size ranges from 20 to 150 microns. Now, in that they have either given the continuous injection of these particles or maybe the pulse injection. The purpose is that when they go inside, their path will be tracked. Normally, we also make it of different colors, so that you can visualize the movement of these inclusions, and either there may be a pulse injection or the continuous type of injection of these particles. Then we need to know that what will be the similarity criteria for this appropriate simulation of the collisions and flotation behavior of non-metallic inclusions in Tundishes. So, that has been proposed by even Sahai and Emi, and basically what happens that there is the collisions of the inclusion particles is also important, because they collides, they become bigger and then they float. So, because that tendency also depends upon the size of the inclusion. So, so for that you have the different criteria that needs to be understood, and especially as we discussed that we need to start from that velocity of fluid for the model, for the prototype, similarly velocity of the rise, that is terminal rise velocity, which it is assumed to go up these inclusions inside the domain. So, that rise velocity. So, if you are doing for the water modeling, so you have the fluid as water. If you do for the steel, you will have the fluid is steel. So, you have inclusions maybe for the prototype and for even for the model. So, then the density difference, what should be those density differences, what should be the size differences, all these things, and what is its bearing on the inclusion flotation behavior or inclusion removal mechanism, that we will try to understand. So, the normally these non-metallic inclusions which we take they are lighter than the molten steel which is found in the steel, and they will be once they go inside, then you will they are, and also they have the varying sizes. So, and also they will be rising with the Stokes velocity. So, these non-metallic inclusions, so they rise with Stokes velocity. It is just assumed that they rise with this absolute velocity. So, you have the velocity of the fluid also, and then you have the rise velocity. So, if you talk about the velocity of the fluid, and in the prototype, so we call it as velocity of fluid in the prototype, that is in the prototype Tundish. Similarly, you will have the velocity of the rise in the prototype Tundish. Similarly, velocity of fluid in the model, and you will have velocity of rise in the model. So, so this you will have the similarity of particle trajectories. That is what you would like to get. So, you would like to have the simulation in such a way that the similarity of trajectories is also found, and for that a condition needs to be satisfied, and that is that V Fm upon Vfp. So, that should be same as Vrm upon Vrp. So, basically velocity of the fluid and that is that and that is within the fluid. So, that and so inclusion will be carried with this fluid velocity. So, that is Vfm, and then Vfp. So, that is for the prototype. So, this ratio should be same as for the rise velocity for model as well as the prototype. So, you will have furthermore certain assumptions, and you will be assuming that there will be Reynolds as well as the fraud similarity criteria being satisfied, and you will be going for reduced scale model, and then what you see that you will try to to go for the appropriate material of the inclusion, which should be taken as the inclusion material for the model, because for the prototype and you also know the liquid that is steel. So, from there the changes in the density of the inclusion as well as of the medium. Similarly, when you know the density of the working fluid in water modeling, that is water, then accordingly you can have you can have a thinking of over what should be the particle which should be taken for the water modeling studies. Similar will be the size considerations. So, what should be the size of those particles that should be maintained, and so that these criterions are satisfied. So, if you take a reduced scale experiment. So, for a reduced scale experiment, so so you based on these fraud similarity assumption. So, what you see in these cases, you get Vm will be Vp into root lambda. So, that is what we have earlier seen, that when you maintain this fraud similarity, you will have the velocity in the model that will be under root lambda times. So, that will be the Vp. Similarly, if you take the length so Lm, it will be lambda times Lp. So, that is what you see when you go for the fraud similarity in those cases. Now, what we do initially in this study, they have it has been reported that the density the density ratio, that is for the inclusion which is taken for the water modeling. So, density ratio between that inclusion to the water. So, it was taken. So, it should have the same density ratio, and also about the size. So, size also appropriately, if you talk about the idealized condition, size should be as per the the geometric similarity. So, it should be reduced by a factor of lambda, but then you have to have the analysis for that. So, if you try to have the same rate of flotation or removal of the inclusions, in that case your ratio of velocities, that needs to be same. So, you need to have that ratio of velocities due to bulk flow in model as well as in prototype. So, that basically that needs to be maintained. So, for that what we do is, if you talk about the bulk flow, liquid bulk flow. So, you will have VFM upon VFP. So, that will be, as we know that the velocity will be basically having the ratio root lambda. So, if you talk about the Stokes rise velocity for the inclusions. So, for the water and for the for the prototype, it is said to be. So, for the for the for the water, that is in the model Tundish, you will have 2 into R inclusion model, and that is square, and then you will have the multiplication with G, and then you have rho of water minus rho of inclusion, that is of in the model, and divided by 9 of eta water. So, that is your V, the Rm, that is Stokes rise velocity, and that is for the model. And similarly, the V for the prototype for that rise velocity. So, that will be can be taken as equal to 2 R, that is inclusion of prototype, that is square. So, that is for the alumina or whatever inclusions we have. Then again multiplied by G into rho of steel minus rho of inclusion in the prototype, and divided by 9 of eta steel. So, for the similarity and for the same trajectory, these ratios what we obtain, that should be same. And if you try to do that, so what we get, so you will have the VRM divided by VRP. It should be same as the VFM by VFP, that is under root lambda. So, it should be under root lambda, and it will be same as. So, once you take the expression of from that earlier expression. So, if you take the ratio, so it will be R of inclusion of model, and that will be square, divided by R of inclusion of prototype, that is square, and then you will have the terminology 1 minus rho inclusion model by rho W, divided by 1 minus rho inclusion prototype by rho steel. So, that is what this ratio is coming. Now, if we take this rho inclusion model by rho inclusion water, so if these ratios are taken same in that case they will be same. So, you will have 1 by 1. So, you will have this radius can be expressed as in the form of the scale factor. So, basically it will be lambda raised to the power 1 by 4. So, that our inclusion for the model will be lambda raised to the power 1 by 4 times R inclusion, that is for the prototype. So, then you can have the selection of the inclusion sizes accordingly. So, so that is what it came. So, if you are considering row inclusion model by row water is same as row inclusion prototype by row steel. In that case your thing becomes like R inclusion model. So, that square and divided by R inclusion prototype. So, that square. So, that will be equal to it is nothing but again you can have the diameter. So, normally we define in terms of diameter. So, you can write again diameter inclusion of model by diameter of inclusion of the prototype. So, they are squares and that will be as under root lambda. So, you can write. So, if you take the again square root on both the sides, you can say that R inclusion of the model, it will be basically lambda times 0.25 and then you will have R inclusion of the prototype. So, this relationship indicates that if you do the water modeling in those cases or even the modeling using the mathematical formulation. So, basically for maintaining that similarity, if you use those if you are eyeing towards the similarity establishment. So, in that case if the if the density ratio is same, in that case the ratio this radius of the inclusion will be lambda to the power 0.25 times. So, R inclusion for the prototype. So, suppose you are going to have the modeling for the inclusion using the water modeling and your inclusion is and you are having a 1/3 scale of the water model. In that case lambda will be 1 by 3 and its power 0.25. So, if you take once its square it will be close to 0.55 and another time it will take so something close to 0.76. So, for a 1/3 scale model the inclusion of the model its size should be about 0.76 times the diameter of the inclusion in the steel. So, that tells you the relationship between the steel inclusion and the inclusion particle which you are eyeing to have the simulation using the or the modeling using the water modeling approach. Now, it may be so that sometimes this row inclusion, so these their density ratios may not be the same. So, that may be different. So, if if your row inclusion of the model by row inclusion of the row of W is not same as row inclusion of prototype divided by row steel. Now, in that case if you look to this equation, if this is not the same. So, what you will get? You will get R inclusion model by R inclusion of prototype. So, that will be basically lambda raised to the power 0.25 because it will be getting the square root on both the sides and you will have 1 minus again the same thing row inclusion prototype divided by rho steel and divided by 1 minus rho inclusion model by rho water, and then you get raised to the power 0.5. That is what you can have this one. So, this will go to that side. So, that will be reversed. So, that will come down for the model, and for the model it will be down, and for the prototype it will be up. So, that way you can have this expression, that is rho. So, then you can have the this rho radius of the inclusion for the model and for the prototype, that will be the kind of the correlationship. So, you can have even a the graph also being plotted, and that graph will tell the relationship between the inclusion in the water model and in the steel. So, that can be obtained, and that has also been obtained by Sai and Emi, and it was seen that if you look at the your this is your model inclusion size. So, that is your dm, the inclusion m, and this will be d inclusion p. So, that is for the prototype. So, in that case, if your lambda is becoming if you have the different lambda, and you will have so if you take the lambda as the 1, so you can have from the earlier expression which we got here. So, these depending upon the different value of the scale factor, you can have the relationship between the diameter of the inclusion which is used in the water model and in the prototype Tundish, that is in the steel Tundish. So, for lambda equal to 1, as you see, it will be the slope of 1. So, it is basically it will be the same graph, and I mean this is this line, and you may have the different values, like if you go for the other values. So, suppose maybe for lambda is 2 by 3 here, then you will have lambda as 1 by 2 or so. So, this way your this relationship can be removed, can be presented. Similarly, it has also been shown that if you take this ratio as a parameter. So, if you take the ratio like if you take 1 minus rho inclusion p by rho steel and divided by 1 minus rho inclusion model by rho water. So, if you take this as one parameter, so you can have a and also if you take this rho inclusion by rho steel. So, in that case if you take certain values, so you can have now in this case, if you know some of this value, so you can have the value of this if you know the lambda, and even you can have a generalized graph which may show the size relationship between the model sizes of the inclusion. So, you will have d inclusion m, and then you will have d inclusion of the prototype. So, in that case, for the particular value of y or gamma, you can say this is y gamma. So, this for that you will have different kind of so you will have 0 to 250 micrometer, and similarly you will have 0 to 200 micrometer. So, in that case you will have a graph like this will be gamma equal to 1, similarly that will be gamma equal to 2, and it has been reported like this will be gamma for 3. So, accordingly for different conditions you will have different type of these graphs by which depending upon the value of gamma you can predict the diameter of the inclusion which can be taken for water modeling if you know the diameter of the inclusion which is used in the steel. So, we will have to further see that when we do the mathematical modeling analysis, in that case you will have these considerations as well as some other considerations to be kept in mind as far as the boundary conditions are there, or the other operating conditions. So, that we can discuss and see the results on some of the case studies which has been carried out. So, that can be done in our coming lectures. Thank you very much.